Alright, hello everyone. It's January 25th. Alright, let's get this done going. We're gonna do this and we're gonna read this. That's basically today's goal. Yeah, that's today's goal. We're not gonna do anything else, just those two. Alright, longest common subsequence. That was an old problem, as old as it can be. Longest common subsequence. Very old. Very old. DP top down is easy, so let's try bottom up. I'm always having trouble with bottom up. So with bottom up, we have A, B, C, D, E, and A, C, E, right? We're gonna have a table. Basically, we're gonna compare longer common subsequence, this, right? And then once this is equal, we'll try the one in front. So we say dp ij is equal to the longest LCS ending at ij, right? Ending at ij. So if text 1 I is equal to text 2j, right? If the two are the same, then the longest will be, we count this and then shall equal to, so dpij shall equal to dpi minus 1 and j minus 1 plus 1. Otherwise, if they're not the same, right? If they're not the same, then dpij shall equal to the maximum of dpi minus 1j and dpi and j minus 1. I think the only thing we need to work on is we need to have a 0, right? So just start with a 0. And when the 0, it should be 0 because you're matching to empty, so it's always 0. Okay, so let's write this. mn text 1 text 2 dp shall equal to, maybe 2 of them is enough, right? Yeah, I think we don't have to get the whole thing. We just need to get a dp and we get another one. Because every time, if it's equal, it's minus 1. Yeah, otherwise it's this or this. So dp, we shall equal to 0 times n. N plus 1, actually. Okay. Then for I in range m, and temp equal to 0 times n plus 1, j in range n. Okay, so maybe it'd be easier if we do, 1 to n plus 1, 1 to n plus 1. Okay, I think this will be easier. And the first row is all 0, so what I'm going to do is just compare to text 2 to text 1, right? And previous will always be 0. Yeah, so we just, if I remember right, it's text 1. I minus 1 is equal to text 2, j minus 1, right? Oh, this doesn't exist. If that's the case, then we say it's temp, because we do ij, temp j, right? Temp j shall equal to dp j minus 1 plus 1. Else temp j shall equal to maximum dpj minus 1 or temp dp, no, I think it's dpj and the temp j minus 1. And then at the end we say dp equal to temp, and at the end we return dp minus 1. I think that shall be it. The good old the good old LCS problem. Let's see if it's right. I went through this very fast. And yeah, I think it's correct. Yep. That'll do it. That will do it. This is one of the first DP problem that I ever done in a class. What are you trying to do? I'm trying to do GB. Python doesn't support block comments. Oh my god. You are right. You are absolutely right. It does not support block comments. I wonder what method I use. This is 1 year, 1 month ago. Yep, that's exactly the same as today. This is 2 years, 3 months ago. Yep, that is exactly the same today. I think every time I thought about the same thing, the top down will be easier, so I should do bottom up every single time. All right, let's read this. So this is coming back to yesterday. This problem has been troubling me for so long, so many days. If we have k groups, we need at least k elements. Solution 1, math. So we use AI to fill this pattern. These are some test cases, right? Take this diagram as an example. For each column, we'll try to fill I with AI times, and each row will form up the group. Wait, hold on. Each row will form, and each column we try to fill. Yes, I agree. Each column, I think I drew something very similar. Each row will not have duplicates. So try to fill the last column with element of bigger limit, and fill the left column, typo, with element of small limit, and that's the reason we need to sort the elements by their limit. Okay? We'll fill from left to right because obviously we don't know how many group we can reach, and then we can also try fill the kth group Then from right to left, this will lead us to binary search solution with complexity. Is that what it's trying to say, to do binary search? Assume currently we already have k groups and x more available elements. We check if we can form the k plus 1th group. If x is smaller than x plus 1, we don't have enough elements, need to wait more elements to come in. If x is larger or equal to k plus 1, we can fulfill the k plus 1th group, but we cannot have the k plus 2th group directly, even we have enough elements, because in n groups, we can use one element at most n times. Those overflow will count it as available elements and can be used as available elements in future. Note that we count this part as available elements, but actually we will use AI. These available elements will be really used when we don't have enough elements. What the hell are you talking about? I guess I'll just read. We sorted for A in A, total plus equal to A. Okay. If total is larger or equal to k plus equal to 1. Isn't that what I had? I remember I have a solution similar to this. It's the count. This is count. This is a type of count. This is how many in total from 1 to k plus 1. This is the total number from 1 to k plus 1. So you're saying we're just trying to see if we can fill if we start from the front, that's the first one, right? If we fill it, and then we fill the second one, we fill it, and then we have some extra, and those extra right, and then for the second one we fill. Oh, hold on, this is slightly different from my way. This is just saying anything that's extra we can use for the next one, as long as we don't put on the same row. And we never have to put on the same row. We never have to put on the same row because we always have something else. So you can always put it, so as long as you can put it somewhere that's not where you put previously, and you can always do that, right? Is that right? But what if you have many of this? This is just required. This is the total number for the next one required. And this is just if my total has enough for the next required. I mean, if we have the next, then we can fill the current one. That's what it means. If we have enough for the next one, then we can fill the current one. I mean, for the first one, yes. If we have enough for the next one, then we can fill the current one. Okay, so we go for the next. Now k is equal to 1, but we're not even looking at the current one, we're looking at the next one. Can we fill the next one? I don't understand why. Assume currently we already have k groups and we have x more available elements. We check if we can form the k plus 1th group. If x is smaller than k plus 1, we don't have enough elements. We need to wait more elements to come in. If x is larger or equal to k plus 1, we can fulfill the k plus. Why can we fulfill the k plus 1th group? Why? What is a 1177? I start with this. Okay. We do 1177 using this algorithm. See what happens. 1177, right? So total is 0, k is 0. So total now is 1. Okay. Total now is 1. And k is 0. So we try to see if the first one can be filled. Because k starts with 0, so we say k equal to 1. K is 0. This is 1 times 2 divided by 2 is 1. This is to fill k plus 1. This is to fill 1. And now we say, yes, we can fill. So k plus equal 1. So k now equal to 1. Coming back up. Next a is 1. Total become 2. Now I need to see the second one. Can we fill the second one? And we can't, because 1 plus 1 is 2. 2 times 3. We require 3, and total is not larger than 3. Which means so far I have 2 elements. And in order to have 2, I need 3 elements, so I need to wait. Okay, so I basically just wait. So wait for the next round. So the next round comes in. I have some. Right, I have a new total. I have a new total. So basically it says at each round, if it's perfect, then we always can just keep going. If it's not perfect, then we always, if it's not perfect, like we have something missing, then we wait. And we wait. And eventually we'll have some that will have enough, then they can come to help here. And the way we analyze this, every time we will do something like this, right? We just stack them like this, and then each row will become right. And based on this, we can always stack the same number, right? We can always stack the same number on this side. So what might happen if I have this? If we have this, like 1, 1, 1, 2, 3, 1, and 4. Well, 1 and 4, you can form 2, because you have this and you have this. This will not be right. Huh? Then this, you form the first one, and you hit this, it doesn't work because currently I have two. And you hit this, it works because you can put one of them here. That doesn't make sense. That doesn't make sense at all. Like, why does it work? Because this is not. He's talking about the roles, right? The roles. And the groups are columns, right? These are the groups. These are the groups. K groups and X small available items. If we check, we can form the K plus 1's group. K plus 1's group. The extra. Okay, so assume currently we already have K groups. And if X large equal to K plus 1, because K is always 0, it doesn't really matter. We can fulfill the. Why can we fulfill? Like, why does this work? Yeah, we try to fill each column. Okay, so basically we'll move to the third one in order to fill 2. Then I'll have, right, 1, 2, I have 6. But on K equal to 2, okay, yeah, K plus 1 equal to 2, it doesn't work. Because the second cannot work, right? But if the second one it works, then it's good. Then we have extra. And then we have the third one. Right, let's say the second one works and we have extra. Then we go for the third one. Yeah, what if we have like... But you can't have the third one if you don't have another value. If you have another value, then The third one. But since you sorted, you always go from small to large. So you find the smallest, and then you have another small. If small can fit, perfect. If small cannot fit, then any remaining, you take it away, right? And then go for the next one. And the next one is not enough, you can put it on top, right? If it's at least the same as the current one, so it won't be any smaller. It won't be any smaller than what you have at the moment, right? So whatever you have at the moment, if it fails, the next one won't be any smaller, so it will be at least the same amount. If it's the same amount, then it will not be enough, right? Because we fill 1, we fill 2, and we cannot fill 3 because we don't have enough to fill 3, right? But if we have extra, then we might fill 3. Well, but if we have extra at the beginning, okay, then those extra can continue for the next one, right? Yeah, I think the reason is as we move forward, right? As we move forward, the values or you can say, like in this case, instead of doing 0, 1, 2, and then like 2, 2, 2, instead of doing this, we pick a different one. So every time we try to fill with a new value, right? Every time we try to fill with a new value, and what we're trying to do is fill with a different value, right? That's 1, and then the next one should be 2, and 2 we have 7, right? So you could have filled this and an extra 2 coming here, or we can say any of the missing, I use the current to fill. Once I fill it, the current, just put it aside. We don't use it until we don't use this value, okay? We don't use that, just 2, because I fill, right? Like we have something, we don't know. I have something, and then we fill with the same V. Once we fill it, that's it for the current one. Then we go for the next one. And the next one we try to fill, but the next one is as at least, right? At least the same as this count, which means it will be more than this. Yeah, it will be more than this or equal to this, because this must have some extra, right? And because we sorted it, it may have a smaller amount. What if S has smaller amount? What if I have smaller amount? The whole purpose is for the other one, for this to not overlap with this, right? We try not to have them overlap. So if I have enough to handle this entire thing, the next one will be able to handle the entire thing at least, right? And I can at least have the other one on top, right? So that will not matter. But if the other one doesn't cover the top, then this one can always put at the bottom, right? Then we can cover. Yeah, if the other one put on the bottom, and then this one will cover, and then we say if this one still doesn't cover, that we simply don't have it. Because the point of having this is add the k, right? The whole point is so that this can stick out. That's the whole point. If we cannot, then we just cannot. So each time we're just trying to add one more to the top. That's it. Each time that's the goal, we add one more to the top. So the next one comes in, we just try, right? We try, and if we have any of the extra, we can always put at the bottom, right? We can put at the bottom until we hit this one, right? Until we hit this one. If we have enough of it, right? If we have enough of it, then we can always do this, and then anything extra we can fill it. It will be the same. If we don't have enough of to hit, that's fine. We hit some, and then we try to fill the others, right? And then if it stick out, that's good. If it doesn't stick out, then we cannot do. If it does stick out anything more, we can always put at the bottom. We can always put at the bottom. So yeah, we go through each one, and for each one we try to fill each column, right? We try to fill each column. So we fill each column, and we fill each column. If it's not enough, that means this one we cannot, so we wait for the next one. And the next one, any extra we use to put in here, and then anything still more, we can leave it here, right? We can leave it here, but it doesn't matter. But that's just we have some extra, right? We have some extra after doing this, but it's fine. The next one come in, and then we add together. We see if we can fill the whole thing, right? If we can fill the whole thing. If we can fill the whole thing, this plus this can fill the whole thing, right? The only one, and then we can always put the previous one at the bottom, and then we put the new one on the top. Now, if we have the previous one, it will extend beyond. So then we have two duplicates. If that's the case, then the new one must be at least will be more than this. We can just put a new one here, right? We can just put a new one here. So any extra in the future, we do the same thing, right? We do the same thing, and a new one will be even. Yeah, this makes sense. This makes sense. Oh, it's a counting sort. First I number. We at least need to prove the following things. Fi is the number of groups using only the first I numbers. If Fi is the number of groups using only this and the number of groups using this, required. Now I have the idea. It'll be easier to draw, right? It'll be easier if we can draw this, but I have the idea too, how this can be proven. So the ideal situation, right? The ideal situation is for each. So when we have the when we sort the numbers, we try to fill each column, right? Ideal situation is each column contains the exact same values. That's the ideal situation. And if it's not, then we'll have a column that has, yeah, maybe we can write is my proof of the line. The ideal situation is that we add each repeated number value to each column, and they fill the max possible for each column. Then each row forms a valid group. For example, 1, 2, 3, 4 will give us so we have 0. We have to use this, right? So it will be 0, 1, 2, 3, 1. No, yeah. This one will be 2. Preview it. Yeah. 3. Now, if there are any extras for any column, we don't have to use it. We don't have to use it because as long as a column can be full, if we have any columns, we don't have to use them. If there are any, to use them. For instance, 1, 2, 5, 10. Right? The difficult part, the tricky part, is when we don't have enough values for a column. And values to completely fill a column. In that case, we'll fill as much as we can, right? As much as we can. then wait for the next value to fill the rest. For example, if we only have, for example, if the current column, right, requires 5 values, but requires 5 repeats, but our current value can only spare 2 repeats. Current value x, right, can only spare 2 repeats. Then we need to wait for the next value y to fill the remaining 3 spots. Right, we have x, y, y, y. Now, for the next column, if there are fewer than, if there are no more than 2 y's left, we can stack them, right, at the same as stack them at the bottom so that they do not overlap with the other y's, right? Do not overlap with the other y's. Overlapping is bad because if a value overlaps, our row will have duplicates. So we have y, y, some z, z, right? In the example below, we have 2 y's and can fill the rest with z. Maybe I should also comment this. X, y, 2 y's left. If the total count of x, y, and z, we can just say we have 2 y's that can fill the rest away with z, so we are able to complete the 6th column. If we don't have enough z, which means the total count of all the repeats, including x, y, and z, do not is smaller, right? Is smaller than the requirement for 6 columns, we cannot produce the 6th column, or which is equivalent, right? Which is equivalent to saying we cannot produce 6 groups, 6 rows, which is the same as saying we cannot produce 6 groups. Now, what if we have more than 2 y's? We are bound to cause overlap, no? Well, not really. If we have more than 2 y's, right, then the total number of y's, total number of y is no less than the max number required for the 6th column, right? And since the repeats are sorted, it is guaranteed that the number of z is also no less than the max number required for the 6th column. Right? In this case, in such case, we don't have to. We can skip. We don't have to even use y, and can rely on z completely to fulfill the 6th column. Right, to fulfill the 6th column. Following the same logic, any extra values from the previous rows can always find their appropriate positions to fill in future columns, right? In future columns. Hence, all we need to check is yeah, because if it's have any more, we just don't use it, right? We just do as much as we want, because the next one will have at least the same amount or even more. Is the total, right? Is the total repeats versus the total required for the groups, for the columns. Right, so this one will be, we say y, x, and then this will be z, plus 2 times y, yeah, with 2 additional y's. I hope this makes sense. It makes sense to me, right? An extra, yeah. We don't have enough values. Wait for the next value y to fill the remaining 3 spots. For the next column, if there are no more than 2 y's left, we can stack them at the bottom. Yes, we can stack them at the bottom so that they do not overlap with the other y's. Overlapping is bad because if a value overlaps, our row will have duplicates. In the example below, we have 2 y's, and we can fill the rest with z. So we are able to complete the 6th row. If we don't have enough z, which means the total count of all the repeats, including this, is smaller than the requirement for 6 columns altogether, right? For 6 columns, for smaller than the requirement for 6 columns altogether, we cannot produce the 6th column, which is equivalent to saying we cannot have 6 rows, which is the same as saying we cannot produce 6 groups, generate 6 groups. Okay, what if we have more than 2 y's? We're bound to cause overlap. Not really. If we have more than 2 y's, then the total number of y is no less than the max number required for the 6th column. And since repeats are sorted, it is guaranteed that the number of z is also no less than the maximum number of the 6th column. In such case, we don't have to even use y and can rely on z completely to fill the 6th column. Following the same logic, any extra values from the previous rows, that's not true. That should be column. Any value from the previous columns, right? Columns can always find that. That's the thing, that any value can always find their appropriate position, right? I have any extra, I can always find that whenever I fill them the first time, we can always find the appropriate position. Yeah, and if we have any more, then the next one will at least fill in. I shouldn't say proof, this is my understanding, right? Understanding. I won't say it's a proof, but it's definitely an understanding. Okay, I'm gonna post this. Okay, so with that, we are going to give him a vote, although he didn't really explain it very well. And then what? Then it's, we're gonna do this one more time. Okay, so we're gonna say this is the solution from for breakdown of this method, refer to my own comment. Copy and paste my comment as well. Okay, copy and paste my comment. Owen login, but without the binary search part. Okay, that should be easy to which is just sort it, right? And basically, what I want to do is to check if it's possible for the current. I might just start with, res result total. Yeah, we have a total is 0, and the rest shall be 1. Isn't rest should be 1, right? I like to go rest equal to 1, and then for u in usage limits. Oh, maybe you would like to entertain this idea. I actually think this is a better idea because I'm not making changes to the original data. So for this, total plus equal to u, right? And if total is when do you, yeah, if total is, because I want to see if the current is possible. If it's possible, then I'll try the next one, right? And then at the end, if total is larger or equal to, I'd like to say 1 plus k, that's the requirement, times k divided by 2, right? That I say res plus equal 1, and it's not k. I did res, right? Result plus equal 1. So we try the next one, right? And if it's not, we just keep adding until 1 is possible and try the next one. Once it's done, I want to return res minus 1, right? This is the possible, right? The possible, we should do it here, is res number of groups possible, right? If it's possible, I try the next one, right? And at the end, when we get out, we never try the res, right? So it should be res minus 1, okay? Oh no, I deleted all the test cases that's been accumulated. I remember we have this 7. Oh, let's pull out all these test cases. Yes, that's a good one. That is a good one too. Yeah. Very good. Very good. I am not putting this problem on a queue because it's solvable, right? With a hint, it's solvable. It's just this idea, just like how you manage to move the pieces around. That's the difficult part. I'll argue we just continue. Okay, that is for another time. That looked like a try to me. All right, that will be it for today. I will see you guys tomorrow. Adios.